All right, so the big idea behind vectors. Vectors are mathematical objects that possess magnitude and direction. Those are the two things that totally characterize a vector. We represent vectors in the plane using a directed line segment. So we've got a line segment. Directed means we got this arrow. And so we haven't really talked about how to quantify these two things, magnitude and direction. We've just sort of been kind of rolling along with intuitively what they mean to us. And so that's kind of what we're going to do today is quantify. So we have an arithmetic of vectors, addition, scalar multiplication, subtraction. Talked about what those meant geometrically. And we talked about what those meant at the level of components. So remember the way we can algebraically represent vectors is by components. So if you got a vector, say going this way, delta x, delta y, that's what we got going on there. It looks like the width here of the pen's a little wonky. Okay, so let's first talk about magnitude. So we mentioned this yesterday. Vectors, doesn't matter their starting point. All that matters is their magnitude and direction, their delta x or delta y. So we can always assume that we can always put the vector, pin the tail on the origin. Okay, make the initial point the origin, and then component. If we look at the components v1 and v2, if the initial point's the origin, then the terminal point's going to be v1, v2, and we can easily figure out what the length of the vector is. Okay, so anyone want to volunteer what theorem this actually is? How are we figuring out the length of this line segment here? Can you see it? So you're taking v1 squared plus v2 squared, taking the square root. So what theorem is that? I'll suggestively do this. Remember the name of that one? That's your Pythagorean theorem. Yeah, Pythagorean. Yep. What's funny is I went to in graduate school, I was sent to a conference in Iowa for budding topologists, and they had this they're big ice-breaking activities. We went around the room, and everyone quoted their favorite theorem. So of course, these graduate students, working on their dissertations, they're quoting all these crazy things. They get to me, and I said Pythagorean theorem, and they thought I was joking. And so they started laughing. I'm like, no, I'm serious. Just think about how, the importance of Pythagorean theorem to civilization and to all the math. It gets everywhere, this theorem. So once again, we're denoting the length of the vector by the norm of v using the double absolute values. The book will just use a single absolute value, and GeoGebra does that as well. We'll talk about GeoGebra here either today or tomorrow. But yeah, that's the magnitude of v. It's literally the length of the vector. Okay. Now, if you think back to polar coordinates or trigonometry, what this says is that if you put the vector in standard position, the terminal point of the vector is going to be on a circle of radius magnitude v. All right, so that's sort of the radius or the distance out from the origin there. So now that we've got, if we put it in standard position here, then we can look at the angle, the counterclockwise angle it makes with the positive x-axis. And once again, if we think of polar coordinates, we know that, and let me draw that triangle in here again. Right? If we call this, x and y, we know from polar coordinates x is equal to r cosine theta and y is equal to r sine theta. Okay, so you can think polar coordinates are really just definition of sine and cosine, really. And so then we can equate the components here. So we get that v1, the x component, the x coordinate here, would be the radius, magnitude of v, times the cosine of theta. v2 would be the magnitude of v sine of theta. And so this gives us a way to think about magnitude and direction. So if I put this in here for my vector v, it's got components v1, v2. But v1 is the length of v, the cosine of theta. v2 is the length of v sine of theta. And so notice the length of v is a number, right? The length of v is a length. It's a real number. It's a scalar. And so we can undo the scalar multiplication here and write this as, and pull out a length of v from each component. You follow? So that's just the number times that. And so this vector here, we think of this vector, this is the direction of v. And we're going to call that v with a hat over it. So we'll talk more about this hat. So this little symbol here is I call v hat. So if we want, as long as the length of v isn't 0, I can divide both. I can do it this way. I'll write it this way first. So this is magnitude times direction. And then we can recover the direction by taking v divided by the magnitude, meaning it's 1 over the magnitude, 1 over the length, times the vector v. So this is how we can get to the direction. But you can see here this big idea that we're going to be using over and over again when we do things is this equation right here. The vector v is its length times its direction. And so that's our definition here. Now sometimes, they'll give you the direction in terms of theta. They'll tell you what theta is from the positive x-axis, or they'll give you an angle from a certain axis, and then from that you can get your cosine and sine and all that other stuff. But this is really the big idea here. If there's one thing you take away from today, it's this. All right. So let's look at properties of magnitude and direction. So first off, the magnitude is always greater than or equal to 0, and the only way the magnitude is 0 is if the vector is the 0 vector to start with. So hopefully that makes sense. Once again, if we think about the magnitude here in standard position, that's the distance from the terminal point to the origin. This is always going to be a positive or 0. The only way this would be 0 is if you're at the origin. Your distance to the origin is 0, which is going to force both v1 and v2 to be 0. So that's a nice property there. For all scalars, if you scale a vector by k, then when you take the length of that, you're going to scale by not k, but the absolute value of k. So for example, we talked about v. All right, let's say you looked at the vector minus 1/2 v. We know that the 1/2 there means it's going to be half as long. And what's the negative do again? What's the negative do? If you multiply a vector by a negative, what does that do to the vector? Yeah, it flips the direction, yeah. So if you think about it, that negative just flips the direction. So if I looked at the magnitude of minus 1/2 v, well, it's going to be half as long as v. You wouldn't say it's minus 1/2 as long. It's half as long as the vector v. And once again, if you wanted to prove this sort of thing, if you started off with v as some generic vector v1, v2, and you looked at k times v, by definition, you're scaling v1 and v2, whoops, by that. Then if I take the magnitude of kv, by definition, the way you get the length of a vector, the magnitude of a vector, is you square the components, you add them up, and take the square root. So this is Pythagorean theorem. And now if we try to simplify that, we could get a k squared v1 squared plus a k squared v2 squared. And now we can factor out a common factor of k squared within the radical. Now, square roots do not work well with addition, but they do work well with multiplication. So I can use the product rule for radicals to write this as the square root of k squared times the square root of v1 squared plus v2 squared. And once again, I'm stuck here. I can't simplify this anymore, but I can simplify the square root of k squared, and that's the absolute value of k. And then we recognize this. You're squaring the components, adding them up, taking the square root. That's then the magnitude of v. So once again, these proofs in this section all come down to doing these calculations in general. And that's all it is, and then using the appropriate properties of real number arithmetic. So a lot of these properties are inherited, once again, from the real numbers. Example 4 here, the solution's written for you. Once again, I don't want to belabor this because it's kind of a pre-calculus kind of a thing. So for example, let's just look at example 1 here. Find the component form of a vector v where the magnitude of v is 5, so that when v is plotted in standard position, it lies in quadrant 2 and makes a 6-degree angle with the negative x-axis. So basically, this is, once again, all you need to recover a vector is you need its magnitude and its direction. The thing you want to be careful about is the direction vector. It's a cosine theta sine theta, but the cosine theta sine theta is always coming from the positive x-axis. So what they tell us here is it has a magnitude of 5, so we know that the magnitude of v is 5. And when plotted in standard position, that tells us that the vector has an initial point of the origin. It lies in quadrant 2 and makes a 60-degree angle with the negative x-axis. So what they tell us is that it lies in quadrant 2, and the angle here is 60 degrees with the negative x-axis. Okay? So that means that the theta we want for the direction calculation is going to be what? It's not 60, but what? What would this angle be? Yeah, 120, good. You follow? So that's the thing, you have to just be careful. And so, you know, the rule of thumb, the mantra I always use is when in doubt, graph it out. All right, just do a quick plot of it. So now we can recover all of this information here. We got the theta is 120 degrees. So once again, v is magnitude times direction. That's 5 times the vector cosine 120 degrees, sine 120 degrees. If you don't have the unit circle memorized, you should at least have it handy. Take a look at it. Cosine of 120 degrees, that's going to be, well, it's a 60-degree reference angle, living in quadrant 2. And so you get negative 5 halves, 5 root 3 over 2. Okay. Now, folks, whenever I ask for something like this, the only time I want to see decimals is that if it's a terminating or repeating decimal. So, for example, if you really wanted to, you could write this as negative 2.5, but don't approximate things unless I tell you to. All right. So if I said, like, if you're doing some applied example and I said I need you to find this to within 2 decimal places, but if I don't tell you to approximate things, don't approximate them. Right? Leave them in terms of their radicals. Number 2 kind of goes backwards. Here's the component form. Find the magnitude and the angle. So let's take a look at this one, and then I'll leave number 3 for you to do. You can do that one on your own, but let's take a look at number 2 here. Once again, these are the standard sort of things you would do in trigonometry. Whoops, what do we got here? It's 3 comma negative 3 square root of 3. Ask us to find the magnitude, and then essentially they're having us find the direction here. So magnitude, the way you find the magnitude or length of the vector, you square the components, add them up, and take the square root. So you got 3 squared is 9, plus negative 3 squared is 9, times 3 is 27. This gives you the square root of 36, which is 6. So remember, when you take the square root of a number, you always get the positive one back. So there's our magnitude. So this vector has a length of 6. Now they're asking us for the angle, direction angle there, theta. So remember, we're always looking from the positive x-axis. So once again, when you're looking at directions, when in doubt, graph it out. So you got v as 3 comma negative 3 square root of 3. So if I plot v in standard position, it's a positive x value, negative y value. So it's going to be down here. Okay, so that's where our v is. And we want our angle theta to start that away. Okay? So it's up to you how you want to solve this problem. This is one of these classic trigonometry type things. We can get the sine and the cosine here. So basically, remember that we could always find v hat by taking v divided by the length of v. So that's 3 comma negative 3 square root of 3 divided by 6. You're like, well, wait a minute, Stitzy. We never talked about how you divide a vector by a number. But remember, there is no such thing as division. You're always multiplying by the reciprocal. So when we write something like this, what we actually mean is we're going to take the scalar 1/6 and then do the scalar multiplication. A sixth of 3 is a half. A sixth of negative 3 root 3 is negative root 3 over 2. And then this is our cosine theta sine theta. And so, once again, it's up to you how you want to handle this. If it's an angle that you recognize, like hopefully you recognize this pair, this is a common pair, then you just, oh well, it's a 6-degree reference angle, which in radians is a pi over 3. So this is a 5 pi over 3 because they wanted it in radians. Oops. So okay, theta is 5 pi over 3. If it's an angle you're not familiar with, you could always go through, divide these two, get the tangent, and then use an inverse tangent or something like that, or inverse sine, inverse cosine. However you want to do it. You can find the v hat, and that's going to give you that point on the unit circle that you can use to figure out the theta. Okay. Any questions on going backwards? So if you're given component form, you can find the magnitude with the Pythagorean theorem. Then you can scale out the vector back to its direction and then get the theta from that point on the unit circle, or what have you. And then you can look at number 3. The solution's all here. Once again, if you have questions on these, just let me know. Example 5 is a classic example of an application of vectors. You've got a plane leaving an airport with an airspeed, 175 miles per hour, and a bearing. And you have a 35 mile per hour wind blowing at another bearing. Find the true speed of the plane rounded to the nearest mile per hour, and the true bearing of the plane rounded to the nearest degree. So once again, I'm not going to go through the details here, but the strategy is you've got the plane setting off with one vector and the wind coming in to try to blow it off course. The way bearings work is you got this compass rose here. So you got north and south, west and east. So if you have a bearing here that's north 40 degrees east, you start at north and then you're going to go 40 degrees towards the east. So this would be what the plane is trying to do, and you got 175 miles per hour. So the angle we typically use, once again, thinking of east as being the positive x-axis, well, that would be 50 degrees. And so if we let v be the plane, the velocity of the plane, then that would be its magnitude, aka speed, 175, times its direction. Okay. And then you could work that out. And then for the wind, is a 35 mile an hour wind blowing at a bearing of south 30 degrees east. So once again, we would start at south and rotate 60 degrees towards the east. And so the angle here we'd be using for the wind would be 300 degrees. And so if I look at the vector W for wind, that would be 35 miles per hour times your cosine of 300 degrees, sine of 300 degrees. And this would give you the component form of V and W. So that would be your components of that. And then when they talk about the true speed and bearing, well, you would need the result of that, right? So you have the velocity of the plane plus the velocity of the wind. So you would add those and get the component form of that, and then you would find the magnitude of that. That would be your true. That would be your true speed, and then you would have to figure out the then the direction angle theta to help you find the bearing. Okay, so that's kind of the overall picture of this. So you go through, and once again, I don't want to spend too much time on that. There's your velocity for the plane. Here's your velocity for the wind. Looks like here we just chose to use the negative 30 instead of the other one there. So notice you're adding the plane and the wind speed. So you're adding the x components and then you're adding the y components. And we're told to round things. So that's roughly what the resultant vector is. So to find the true speed, we need the magnitude of the velocity here. So the v plus w and the magnitude, we square the components, add them up, take the square root, roughly 184 miles an hour. And then here's an example where these are points x and y on the circle. Going to use the tangent, y over x, and then use the inverse tangent there to get our 38 degrees. So here's sort of the picture of what's happening here. You can see that the wind is blowing this way, so it's going to move the plane a little bit that way. It's going to go a little bit faster, but it's not going to go at that right angle there. Okay. So do you see the benefit of the magnitude and direction pieces? So from magnitude and direction, you can get to the component form. And once you're in the component form, it's easy to do the algebra, adding and subtracting, whatever. And then taking the component form and going back into the magnitude and direction. So this is one of the classic examples we do in trigonometry that shows you the advantage of each of those different representations. All right. So once again, I just kind of gave a quick overview of it. If you get in there in the details, if you have questions, just let me know. Okay, unit vectors. Okay, so when you see the word unit, like for example, unit circle, this is probably the other time you've seen the word unit. A unit circle, right, or the unit circle, I should say, x squared plus y squared equals 1. It's called a unit circle because the radius is what? So what makes it a unit circle? Yeah, radius is 1. So anytime you see the word unit, it means it has to do with 1. Like for example, the number I is sometimes called the imaginary unit. Okay, so unit circle means radius is 1. Unit vector, a vector v is called a unit vector if the magnitude of v is 1. And if you think about it, that means that if you put it in standard position, its terminal point will lie on the unit circle. Right? So unit vectors are essentially, they're just really the directions because they get tied into these angles theta. So if you're on the unit circle, and so typically we use the notation hat, the hat notation, to denote a unit vector. So if you see a hat running around, that communicates that this is in fact a unit vector, which really means it's the same as a direction. Length 1, it's a direction. So unit vectors are the same as vector directions. And so this process we've talked about, we've got the v is its magnitude times its direction. In other words, the direction is the magnitude divided by, the vector divided by its magnitude. We can think of dividing by the magnitude as scaling the vector back to the unit circle, or depending on if the length is bigger than 1 or less than 1, blowing it out to get to the unit circle. But basically, this process is called normalization. So when you normalize a vector, you're basically distilling the direction of the vector. Okay? So to normalize a vector, You take the vector divided by its length. Now, this works perfectly fine as long as you're not trying to divide by what? Okay. We know that the length of a vector is 0 if and only if the vector itself is the 0 vector. So that means that obviously the length of the 0 vector is 0, but moreover, the only time you get a magnitude of 0 is if the vector is 0 to start with. So this goes back to a question we had yesterday. What is the direction of the 0 vector? So the 0 vector, remember, is represented by a point. You put that in standard position, you just get the origin. So the direction of the 0 vector, that's just plain up undefined. Because in a way, if you think about it, it could have all the directions. You follow? Because the 0 vector would be the length of the 0 vector times the direction of the 0 vector. No matter what vector you put there, the magnitude of the 0 vector is 0. You're always going to get the 0 vector back. You follow? So it's kind of like indeterminate form 0 over 0 kind of nonsense going on there. But the 0 vector is undefined. So you can't normalize the 0 vector. You can't divide the 0 vector by a number and get 1 out of it. You follow? So that's the only vector without a direction. All the other vectors you can normalize to get their directions. Yeah, well, the 0 vector is important. It plugs an algebraic hole in the arithmetic, as we'll see in a minute. So, like in physics, Derek, it's a good question. In physics, if something is in what's called static equilibrium, right? And there's an example here at the end that I'll have you look at. It's like we're hanging a speaker or something. Okay. Then the sum of the forces, all the forces to be in static equilibrium, in other words, to make, so, because if it's not moving, then all the forces have to equal 0. So the 0 vector is an important, plays an important role in the arithmetic and the algebra of the vectors. Does that answer your question? That's one reason we have it. Yeah, good question. Now the two famous unit vectors we'll be looking at are I hat and j hat. So I hat is the vector 1, 0. J hat is the vector 0, 1. And if we plot these in standard position, so I hat start at 0, you go 1 unit in the x direction and that's it. J hat start at the origin, go 1 unit. And so we can think of I hat as being, this is the x direction, and this is the y direction. And what's nice about the x and y, they're at right angles to each other. So, and we'll make this more precise later in the week, they don't really interfere with anything. If you're going left and right, you're not going any amount of up and down. And if you're going up and down, you're not going any amount of left and right. And so we have this decomposition theorem, which doesn't seem like a big deal right now. But we're going to generalize this decomposition theorem here later in the week. So if you think of V, the way we write it in components as a V1, comma V2, the V1, remember, that's your x direction, V2 is your y direction. So you can write this as V1, comma 0 plus 0, comma V2. So you're going right, then you're going up. I mean, this is literally, going back to yesterday, we went this way. Let's see how I'm going to be consistent with the colors here. I was doing red and then blue. Okay, let's do that. Whoops. To be consistent here. So we're going this way. So we're going over and we're going up. So think of this as V1 times 1, 0 plus V2 times 0, 1. So this is V1 I hats plus V2 j hats. And so you're basically taking this vector and you're resolving it into these orthogonal or perpendicular components. Okay? So if you take in physics, resolution of forces or resolution of vectors, this is a big deal, and we'll talk more about it later when we have things that aren't as friendly as I and J. But there's really two big themes in math that I kind of harp on throughout the courses I teach here at Lakeland. There is analysis and there is synthesis. An analysis is you take something complicated and you break it down into basic parts. So examples of this are when you factor a number. You take any natural number, you can factor it into primes. Now, if you understand how those primes work and you understand how they get put back together, then you understand the number, and that synthesis is combining the parts. So breaking things down is analysis. Synthesis is putting those parts back together. And a big idea in mathematics is understanding how the basic parts, how their properties combine to give you properties of the more complicated thing. So what's nice about this kind of idea is we're breaking two dimensions and looking at basically one dimension at a time, which is a huge theme here in Calc 3. When we go do derivatives and integrals and stuff, we're going to see this over and over and over again. So I like to point this out, and you'll hear me mention this over and over again, because it's one of the big ideas that I want you to take away from the course. All right. I'm not going to care if I run into you 5 years from now and you can't tell me how to do a triple integral. Okay, whatever. But if the big concepts have stuck with you, you know, especially if you're off using them out in what you're doing, that's great. And so here's what's happening here. Here's the picture that goes with that. You got your I hat, and then you scale it by the V1. You got your J hat, you scale it by the V2, and then you add those together, there's your resultant. And so Derek, here's the example I was mentioning earlier. You got a 50-pound speaker is being suspended from the ceiling by two support braces. If one brace makes a 60-degree angle with the ceiling and the other one makes a 30-degree angle with the ceiling, what are the tensions on each brace? So what you have is you've got 3, 4. Now you're assuming that this thing isn't moving around or anything. So you've pretty much, in order for this to stay put, you've got 3 forces here at play. You've got the tension on this wire, which is a force because it has a magnitude and a direction. You've got a tension on this wire, and then those tensions are counteracting the weight. So they're asking for the tensions on each brace. So when they're asking for the tensions, you know, how much force is each of these wires, what's the force that they have on them? They're looking for the magnitude. So basically looking for the magnitude of T1 and the magnitude of T2. And so what you do is you have these things, you're looking for magnitudes, but you're given directions. And so you make this little force diagram here. And so you can get the vector T1 would be whatever that tension is, the magnitude of T1, times the direction. Well, the direction here, if we call this the positive x-axis, then the angle there we're looking at is 60 degrees. Okay? So we don't know what this is, but we do know the angle. And likewise with T2, right, if we call that there, we know that this is 30 degrees. So we know that that would be 150 degrees. And so here's what we can get for that, for T1. magnitude times direction. And here's what we can get for T2, magnitude times direction. Now we're after the magnitude of T1 and magnitude of T2. And so here's where we use the zero vector, Derek. Since that speaker isn't moving around, the sum of those forces have to be 0. Now, what's the weight vector, W? Well, the weight is acting directly down. So the weight vector would be 50 times the direction. Well, it's directly down, 0 minus 1. Or think of it as minus 50 j hat if you want. 0 minus 50. So if I add up T1, T2, and W, it should be 0. So that's the physics principle here. And how do we add vectors? We add them component-wise. So here are the vectors, and now we add them component-wise. And now we have the equality of vectors. When are two vectors equal? They're equal when the corresponding components are equal. So we're going to set the x component on the left equal to the x component on the right. And then the y component on the left equal to the y component on the right. Okay. So you're following along the logic here. Do you see how we're using vectors, magnitude and direction, and then how we're getting this into an algebraic system? And then we just, do substitution, elimination, whatever you want, and then we can recover the T2. The tension here on T2 is 25 pounds, and on T1 is 25 root 3 pounds. So notice when you add those numbers together, you get something more than 50. Well, that's because the 50 is only being counteracted by the vertical components here. All right, and since they're at angles, they don't quite add up. All right, you're going to have the tension is going to be bigger than because there's some of it going in the horizontal direction. Okay, and once again, I don't know how they do this in physics class. This is how I like to think about it. But if you go back and like I said, if you go at the plane example and then this example and you work through the details, hopefully you'll get an appreciation for, once again, the big idea. If you take nothing else away, a vector v is its magnitude times its direction. This can help you get to the vectors, right? This will help, and then so then you can use this to get the component form. And once you get the component form, you can do algebra, and then you can turn it back into this form. And sometimes we call this, I don't know if I mentioned this. Sometimes I call this the polar form because it's like the r and the theta from polar coordinates. Because it's basically v hat tells you sort of the angle, and then the magnitude tells you how far out to go. So sometimes I call this the polar form. So if I haven't mentioned it, there I have. But polar form to component form lets you do the algebra more easily, and then the algebra back into the polar form can help tell you about the physical situation. So it's the idea of changing forms, breaking it down into its constituent parts, the analysis of it, and then the synthesis of putting it back together to see how they both connect. So even though this is a review topic, I like to spend a couple days on it because I kind of want to focus on the big ideas that we're going to see over and over again. Okay? Now, here's the homework. It's from the book. Now, the mentor students, I got the codes for you. I sent you the codes for the book. I ran into Meredith at the bookstore, and she's still trying to get a purchase order for some of the other CCP students. But remember, you can just hop over to the Lakeland Library and check these out for free. I think they're open till 8 o'clock tonight. Double check that. I think they're open till 8 o'clock tonight. But anyway, I don't collect the homework. That's practice for you. You do as many of those as you need to. You can check it out for free. Yeah, they're open till 8 o'clock tonight. You just blast in there, tell them you need to check out a calculus book. They might ask you for your Lakeland ID so they can check it out to you, but you should be good. And I will mention this. We have like a minute left. There is a link to the two-dimensional GeoGebra calculator. And you can write vectors here. Like if you want to write v, one way you can do it, like if you want to have the vector in standard position, you just have to type in the terminal point, and it'll plot it for you. If you want a vector between points, you just type in vector parentheses. Whoops. Now the thing about GeoGebra is it tries to be helpful, and in being helpful, you got to be careful with. So parentheses. If you want the vector from say 1, -2. Type that in. Initial point, terminal point. 2, 4. All right. You can add the vectors v plus w. You can find the length of the vector. You can do -1/2 times a vector. Okay. Now we're going to be using GeoGebra mainly in 3 dimensions, okay, which is what we're going to do tomorrow. So tomorrow we've done vectors in 2 space. Tomorrow we jump into the 3rd dimension. GeoGebra is going to be especially helpful for us in 3D. We're going to talk about, it's sort of anticlimactic to be honest, because we're just going to slap on a z-axis at a 90-degree angle with the xy plane. So GeoGebra is going to be helpful for us visualizing that. All right. Okay, thanks for coming, folks. I appreciate you tuning in. Make sure you do that test 0 so I can document attendance for you, and we'll see you tomorrow.